This video is a tutorial for the Unit 7.5 Quia assignment, The Shape of Small Molecules worksheet. If you're watching this video, you should have already seen the notes video that was assigned from the previous day since it covers hybridization. So if you have not already watched that video and taken notes, I suggest that you save this for later and then go back to that. For our first question here, we're going to be matching up some terms and definitions. So I'm going to be going from the right side and then picking the correct term based on that. For the first one, we have the name of a flat molecule with 3 bonding directions and no lone pairs. So if you were going to actually draw this out, we have an atom in the middle, we have our 3 bonding directions with atoms on the end, and there's no lone pairs to alter the angle of this bond, so this would be a trigonal planar shape. So A. The second one, the type of hybrid orbital in a trigonal flat molecule. So essentially what you would have here. Now, for hybridized orbitals, they are based on how many bonding directions you have. So if I have 3 bonding directions, that means I would have needed an s orbital and then 2 p orbitals in order to make that many bonding directions. The trick to this is if you add the 1 s orbital plus the 2 p orbitals, that equals 3 potential bonding directions. All right, so we are looking for sp2 hybridization, which is down here. The next one, the geometric angle between 2 adjacent bonds within a molecule. This would be considered the bond angle. So we've done A, B, and C. 2 valence electrons which are not involved within a bond. So we've talked about this for a while since we first started doing our Lewis dot diagrams. These would be a lone pair. And lone pairs do have an impact on the overall shape of the molecule. A 3-dimensional visual model of molecular geometry. I haven't used this term yet in class, but this is called the ball and stick model because you're using the little plastic balls and the sticks in order to connect different atoms together in order to make your various shapes. This would be the same as what we were using in the PhET simulation. A hybrid orbital which combines 1 s and 1 p orbital. Well, if you only have 1 s and 1 p orbital, it's got to be this one right here. So this is going to be F. And then for our last one, pairs of valence electrons are arranged as far apart as possible within small molecules. That's going to be G. We know that VSEPR stands for valence shell electron pair repulsion theory. So the electrons are pushing away from each other within their respective pairs. Now just be careful, I don't know if this question was randomized or not, so yours might come up in a different order. So if they don't match with the exact letters, make sure that you are looking at whatever combination you have on your assignment. All right, for our next set of questions, we need to draw a Lewis dot diagram first, and then try to figure out the electron, molecular geometries, and then the bond angle based on that. Now, for a Lewis dot diagram on water, you have your oxygen atom, which has 6 valence electrons around it. So I spread out my electrons before doubling up. I have 2 hydrogen atoms that are going to come in and bond. So I have either a diagram that will look like this, or if I want to draw it a little bit more neatly with the individual lines representing a bond, I could show it like that. Now, in order to find the electron geometry and molecular geometry, you could look at that VSEPR sheet that I gave you in class. When you take the quiz, I have a PDF that I will post to Google Classroom in case you lost your copy. For right now, I'm just going to skip over to this page right here. So for that combination, we had 2 bonding directions on the water and then 2 lone pairs. That's a total of 4 electron groups. So that means that my electron geometry is going to be tetrahedral. And then here where it says geometry name, this is the same thing as saying your molecular geometry. So since we're going with this combination right here, it looks like we're going to have a tetrahedral electron geometry and then a bent molecular geometry. Bond angle is going to be approximately 109.5 degrees. So for this one, we have tetrahedral. This is going to be bent. And this is 109.5 degrees. Now, technically, the bond angle is not actually 109.5 degrees. We talked about this in class as well. These lone pairs are going to push down on these bonds, which decreases the bond angle by a little bit. The actual bond angle for this one is going to be 104.5 degrees. I would accept either answer since this number was technically in your notes, but I wouldn't expect you to memorize it. So if this was the quiz, you could say 109.5 and that would be perfectly fine. All right, for our next molecule here, we have CHCl3. So I'm going to have a carbon in the middle with 4 valence electrons. I have a single hydrogen. And then I have my 3 chlorines that are going to bond around it. So that's my Lewis dot diagram. Again, if I wanted to draw it a little bit more neatly, I could use the individual lines. These chlorines do have lone pairs on them as well, but the lone pairs are not going to have any kind of impact on the shape of the molecule because they are not on the central atom. All right, so again, we look back to our VSEPR sheet. This time it looks like we have 4 bonding directions and no lone pairs on the carbon. So I'm still within this family, which means I have a tetrahedral shape, 109.5 degrees again, but this time is also going to be a tetrahedral for the molecular geometry name. So tetrahedral for the first one, tetrahedral for the second, and then for the bond angle, 109.5. All right, for our next molecule, we have Bi3. Notice that this does break the octet rule. So that means that your boron will have either more or less than 8 electrons around it. In this case, it's going to have less. Your boron is going to start with 3 valence electrons around it. And we have 3 iodines that each need 1 more electron. So I'm going to take the iodine, there's the 6 electrons there, there's the 7th, and then we make that connection. I'm going to do that for each of these sides. If I wanted to space it out a little bit better, I could draw it like this. All right, so I have 3 bonding directions on the boron. Because it's not following the octet rule, there's no lone pair here. So that means I'm going to be within a different family on my chart. So there are 3 total electron groups. That means the electron geometry is going to be trigonal planar, bond angle of 120 degrees. And because it's 3 and 0, that means that I have a trigonal planar molecular geometry as well. So whenever you're kind of at the top of the family where there's no lone pairs, these 2 names are going to match up. For this one in the answer key, I think I have it in there 2 different ways. I'm just going to confirm to check right now. Yes, I do. So you could either type it in as 120 or 120.0, and both will give you the correct answer. You do not want to include a degree sign. All right, next up, we have NH3. Our nitrogen within this ammonia is going to have 5 valence electrons around it. We have 3 hydrogens that are coming into bond, so they are going to connect to each of these sides. So in this molecule, I'm going to have 3 bonds, but I also have a lone pair. So this is different from the previous one that we had done. That means that there are a total of 4 electron groups because there are 3 bonds and then a lone pair. It's part of the tetrahedral family. Bond angle of about 109.5. It's actually going to be a little less because of that lone pair. But now I'm in this category right here, which means trigonal pyramidal. So for the electron geometry, this is part of the tetrahedral family. This is trigonal pyramidal. Not to be confused with trigonal planar. They are different. And then for your bond angle, again, we're going to say it's approximately 109.5 degrees, even though it is actually a little bit less than that. Technically, you could also say it's 107 or 107.0, since the lone pair is going to decrease that bond angle. All right, for our final set here, we have carbon dioxide. So you're going to have a carbon in the middle with 4 valence electrons. We have an oxygen on either side, which has 6. We start with our initial connection here. And then none of these atoms are currently following the octet rule. This oxygen has 2, 4, 6, 7. Carbon has 2, 4, 5, 6. And the oxygen on this end has 7 as well. The only possible way to fix this is to move my electrons into the center to make additional bonds. So if I was going to redraw this, then that means I'm going to have a double bond on either side of the carbon. Each oxygen is going to have 2 lone pairs worth of electrons. So looking at this picture, I have 2 bonding directions. Remember, a double bond only counts as 1 bonding direction. And there are no lone pairs. So if I look at this chart, that means there are a total of 2 electron groups, which means it's a linear shape, bond angle of 180, and it's also going to be a linear molecular geometry. So we have linear, linear, and then 180. All right, so that concludes this tutorial video. If you have any additional questions, please feel free to reach out to me through the mailbag, and I will get back to you as soon as I can.